Microwave tubes, Klystron amplifiers, third and last part, series on microwave engineering, lecture number 4.13. Klystron amplifiers are amplifiers, microwave amplifiers. They are associated with a certain amount of gain, voltage gain. Gain is an important parameter for any amplifier circuit, including Klystron amplifiers. In addition to voltage gain, in the present session, we discuss about mutual conductance, equivalent circuit, beam loading, tuning mechanisms, etc. in the present session. Two cavity Klystron amplifiers are narrow banded. The reason for their narrow bandedness is usage of cavities, which are resonant circuits. Sometimes the need is more bandwidth. Then how to increase the bandwidth of the amplifier, Klystron amplifier? It is done by employing stagger tuned cavities, inserting them in between input cavity and output cavity. It results in multi-cavity Klystron amplifiers. These amplifiers, multi-Klystron amplifiers, they are able to provide more power, more gain. Also, of course, then all the cavities in the circuit must be tuned to one single frequency. All these aspects, they are considered for discussion in the present session. Now let us move to the core session. We begin with the voltage gain. By definition, voltage gain is the ratio of a fundamental component of induced voltage in the catcher cavity to the amplitude of the input signal in the input cavity gap. Notice this is the definition that is applicable to Klystron amplifiers. In general, gain means output by input. Voltage gain means output voltage by input voltage. That's all. That is most general one. But here, not all voltage. Fundamental component of induced voltage in the catcher cavity to amplitude of the input signal in the input cavity gap. Mathematically, AV is V2 by V1 amplitudes. When applied to two cavity Klystron amplifier, it becomes AV is equal to beta naught I2 by V1 RSH. A little bit of manipulation gives beta naught square theta naught J1 X by X R shunt by R naught. Now, what is beta naught? Beam coupling quotient of the catcher cavity. I2, amplitude of the fundamental component of the beam current at catcher cavity. V1 is amplitude of the input voltage. R shunt, RSH, is the equivalent resistance of the output cavity. It can be manipulated. It results in beta naught square theta naught. Theta naught is grid gap transit angle. J stands for Bessel function. One is order. X is bunching parameter. R shunt, equivalent resistance of output cavity. R naught is DC beam resistance. Another parameter, mutual conductance. The mutual conductance GM by definition is ratio of fundamental component of induced current in the catcher cavity to amplitude of the input signal in the input cavity gap. Mathematically, it is GM is I2 induced by V1. Induced output current by input voltage, it turns out to be theta naught square theta naught J1 X by X 1 by R naught. One can easily notice the relation between GM and voltage gain. AV is GM multiplied by RSH. Here, equivalent circuit of the output cavity is shown. It consists of a parallel combination of three resistors representing wall resistance RSHO, beam loading resistance RB, and external load resistance RF. These three in parallel represent the equivalent of output cavity. Of course, current induced is beta naught I2. Now these three can be combined into one resistor, that is RSH. In A is the equivalent circuit, somewhat elaborate. In B is simplified one. The generation of an electronic admittance between two grids of a cavity when an initially unmodulated beam of electrons is shot across the gap between them is called beam loading. Now we are for a discussion on beam loading. There exists interaction between beam and cavity. The amount of interaction, it is described by beam coupling quotient to some extent. Some more information can be obtained by another parameter, beam loading. The generation of an electronic admittance between two grids of a cavity when an unmodulated electron beam is shot across the gap. It is called beam loading. The loading of the cavity by the beam. This admittance is a complex quantity having both real conductive component and an imaginary susceptance component. Admittance is a complex quantity, so it has a real part, an imaginary part. Real part is conductance, imaginary part is susceptance. Conductive component of the loading admittance can be found equal to I naught by V naught theta g square by 24, everything multiplied by 1 minus theta g square by 15. Here I naught is beam current, V naught is voltage by which beam is accelerated. Theta g is grid gap transit angle. The symbol used to represent conductive component of beam loading admittance is capital GP. The susceptive component can be found equal to I naught by V naught theta g by 12, 1 minus 3 theta g square by 20. The symbol for this susceptive component is BB. Some more points regarding beam loading. The conductive component can be positive or negative. Positive indicates that the power is being delivered to the beam by the gap voltage, as happens in case of input cavity in the Klystron amplifier. When the voltage source is a resonator, positive beam loading conductance reduces the Q of the resonator and consequently broadening its tuning. Negative indicates that the beam is delivering power to the source of alternating gap voltage. This is the situation that occurs at the output. If the source of alternating gap voltage is resonator, it may go into oscillations. Susceptive component affects the resonance frequency of a resonator connected across the gap and therefore causes the frequency of an oscillator to change with the beam current and voltage. Now, tuning. What is tuning? It is mechanism by which one can vary, one can change the frequency of operation of a device, an amplifier. What is the mechanism that is there, that is incorporated in Klystron amplifiers to change its frequency of operation? That particular aspect we discuss under tuning. Tuning can be affected with a flexible wall in the cavity. It is simple method. Tuning range is small, 2 to 3%, which is a drawback. Tuner life is limited, another drawback. Flexible wall is a simple method, but it is associated with drawbacks. Small range, limited life. Tuning can also be affected with a movable capacitive element in the cavity. Can give up to 20%, 10 to 20% bandwidth. It suffers with a reduction in bandwidth at low frequency end of the tuning range. It is also associated with certain shortcomings, even though it gives somewhat more variation than the previous method, which uses a flexible wall. Tuning can also be affected with a sliding contact movable cavity wall. It gives a variation of 10 to 15%, but it is complex mechanically. A few points regarding bandwidth. The frequency of Klystron amplifiers is determined by the resonant cavities. which are high Q tuned circuits. Hence, bandwidth is low. This fact is mentioned several times. Now, a brief comparison of this device with its competitors. Klystron amplifiers are better placed when compared to other microwave tubes in producing high power with respect to their geometry. Various regions where beam formation, RF interaction, beam collection, etc. take place, they are all separate and independent. Thus, each one of them can be designed to give their best independent of others. In addition, the design flexibility available with the Klystron is not present in other tubes. So, there exists certain convenience in the design of Klystron amplifiers. Each section can be designed to give its best performance, independent of other parts in the device. It leads to having a device ultimately that performs best. This kind of flexibility doesn't exist in other microwave tubes. Now we go to another aspect of Klystron amplifiers. So far we considered Klystron amplifiers with two cavities. One cavity to accept the input signal, another cavity to deliver the output signal. The performance of a two-cavity Klystron amplifier sometimes may not be adequate in terms of gain, in terms of output power, in terms of bandwidth. In such cases, to achieve higher levels of performance from the Klystron, some more cavities are introduced in between input cavity and output cavity. These are called intermediate cavities. Then the resultant structure, the resultant Klystron is called multi-cavity Klystron. Now, a few important points regarding multi-cavity Klystrons. They are given as introductory points. Now, multi-cavity Klystrons are able to provide more bandwidth, more output power, more gain. Not all, one only. They are able to provide more bandwidth or more output power or more gain. In two-cavity Klystrons, the bunching process is not complete and hence their gain is not large. In multi-cavity Klystron arrangements, things are set in such a way that bunching becomes almost complete and hence they are capable of giving more power gain than two-cavity Klystrons. Structurally, there exist several intermediate cavities in between the input and output cavities. The number of intermediate cavities is not usually more than 5. In multi-cavity Klystrons, each one of the intermediate cavities is placed at an optimum distance from their respective previous cavities. This distance becomes lesser and lesser from input to the catcher cavity because distance is inversely proportional to signal strength in the previous cavity. Because of increased dense bunch formation, the signal strength in each cavity increases from input to the catcher cavity. The net result is in the decrease of optimum length of drift space or the distance between the cavities. Net result is spacing between consecutive cavities diminishes in multi-cavity Klystrons. Two aspects one has to keep in mind regarding multi-cavity Klystron amplifiers are one, the bunching process. It is done more intensely with the help of intermediate cavities, resulting in very thin, highly dense electron bunches. When bunches are thin, when bunches are highly dense, they are able to transfer more power to the output cavity. First point. Second point, the distance between cavities diminishes as we move from input cavity to output cavity in multi-cavity Klystrons. Here is shown the structure. This is the electron gun. It emits electrons, input cavity, output cavity, intermediate cavities. the distance between the cavities, it is not uniform. First it is L1, then L2, then L3. You see here L3 is less than L2, less than L1. These are magnetic coils. The purpose of these coils is to prevent the electron beam from spreading out or to confine the electrons to beam. Collector, cooler. So these are all the things. Signal input is given to input cavity through a current loop. Output is taken from the output cavity through another loop. Now, a few points regarding tuning of multi-cavity klystrons. All cavities are tuned to one single frequency. Then we say klystron is synchronously tuned. With this type of tuning, largest power gains are achievable, but bandwidths are very low, perhaps a fraction of 1%. To achieve greater efficiency, klystrons are operated with intermediate cavities tuned to outside the pass band on the high frequency side, resulting in improved electron bunching. This type of tuning results in gain reduction of about 10 dB, but greater efficiency and increase in 15 to 25% output power. It is told multi-cavity klystrons employ intermediate cavities. If these intermediate cavities all are tuned to a single frequency, then this case is referred to as synchronous tuning. Under synchronous tuning, multi-cavity klystron amplifiers, they are able to provide larger power gains, but bandwidth of the device becomes very narrow. Another type of tuning is also there. It is called stagger tuning. The intermediate cavities here are tuned to off-center frequencies to achieve larger bandwidths, but at the cost of gain. In practice, stagger tuning of multi-cavity klystron results in an increase of bandwidth from a synchronously tuned bandwidth of 0.25% to more than 5%. When the tuning of intermediate cavities is synchronous, then bandwidth is very small, approximately 0.25%. But we adopt stagger tuning, then bandwidth becomes 5%. But notice, stagger tuning leads to gain reduction. Multi-cavity klystrons can be designed with bandwidths more than 10 to 12%. Here are given typical values of various parameters pertaining to multi-cavity klystron amplifiers. One can achieve a power gain of 40 to 50 dB, a bandwidth of several percent. Already mentioned, 10 to 15% is quite common. Frequency range of operation is 0.5 GHz to 14 GHz. Power range is 25 kilowatt to 40 megawatt. These are the things which I have to share with you for right now. To recap, voltage gain, mutual conductance, tuning mechanisms, beam loading are introduced and described in an elaborate manner. In addition to multi-cavity klystron amplifiers, their synchronous tuning, their stagger tuning in the present session. Hope you have a fruitful, a beautiful, a successful, a transformative and enriching learning experience. Enough for now. See you soon again in another session. Bye bye.